Good morning everyone. My name is Devendran, son of Samantha Murthy, and I am from class TKA 3B. Today I will be presenting on fundamental principles and applications of momentum in pipe flow analysis. Momentum in fluid mechanics is the product of a fluid's mass and its velocity. When fluid flows through pipes, valves and nozzles and change in speed or direction creates forces on the pipe walls and fittings. The purpose of this presentation is threefold. The first one is to explain the basic principles of momentum in fluids. The second one is to discuss how momentum applies to curved surfaces such as turbine blades and pipe elbows. And the third one is to show real engineering application in pipe bends and elbows. Finally, I will explain how understanding momentum contributes to safety, design efficiency, and sustainability in civil engineering. Newton's laws and fluid momentum. To understand fluid momentum, we recall Newton's laws of motion. The first one is Newton's second law states that the rate of change of momentum of a fluid equals the net external force on it. In formula form, this is force equals the derivative of mass times velocity with respect to time. This means that whenever a fluid changes its velocity, a force must act on it. Newton's third law tells that for every action there is an equal and opposite reaction. So when a fluid pushes on a pipe wall, the wall pushes back with the same force. Together, these laws form the foundation of the momentum principle in fluid mechanics. For slide 4, momentum principle in fluids. The momentum principle applies Newton's laws to flowing fluids. For steady, incompressible flow, the net force on the fluid equals the rate of change momentum between the inlet and outlet. We assume steady flow, incompressible fluid, uniform velocity across sections, negligible body forces like gravity. This principle helps engineers calculate forces acting on pipe, fittings, valves, nozzles and bends. For the slide 5, effects on forces in fluid flow. When fluid flows through a pipe system, several forces act on it: pressure forces, momentum forces, reaction forces. If the flow changes direction, such as at a bend, these forces creates reactions on the pipe structure. Understanding these forces allows engineers to design safe and strong systems that can handle the stress of flowing fluids. For slide 6, now let's move to the calculation part. When a jet of water strikes a curved plate, its direction changes but its speed remains almost the same. This change in direction causes a change in a moment, which produces a reaction force on the plate. We are given mass flow rate in 10 kilograms per second. Velocity of the jet is 15 meters per second. Angle of deflection is 120 degrees. First, we find the velocity components of the jet. Horizontal component Vx is velocity multiplied by cosine of the angle. That is 15 times cosine of 120 degrees, which equals negative 7.5 meters per second. Vertical component is velocity multiplied by sine of the angle. That is 15 times sin of 120 degrees, which equals approximately 12.99 meters per second. Next, we calculate the force components on the blade by the fluid. A horizontal force Fx equals mass flow rate times change in the horizontal velocity, 10 times negative 7.5 minus 15, giving negative 225 Newton. Vertical force equal mass flow rate time change in vertical velocity, 10 times 12.99, giving approximately 129.9 newtons. So the force on the blade has two components: horizontal negative 225 newtons, vertical 129.9 newtons. The resultant force magnitude is the square root of the sum of the squares the components. Square root of negative 225 squared plus 129.9 squared, which equals approximately 260 newtons. The direction of the resultant force is the arc tangent of vertical over horizontal force. Arctangent of 129.9 divided by negative 225, which equals to negative 30 degrees. This means the force acts 30 degrees above the horizontal in the opposite direction of the jet. Therefore, the reaction force on the curved plate is approximately 260 newtons. This shows that when the water jet changes direction, it exerts a strong forces on the plate. This is the same principle used in turbine blades, deflectors, and pipe elbows. Slide 7. Applications in pipe bends and elbows. In real engineering systems, fluids often flow through bends and elbows in pipelines. As the fluid changes direction, its momentum changes, creating a resultant force on the pipe bend. Engineers use the momentum principle to determine both magnitude and direction of that force and design supports and anchors strong enough to hold it. For example, in water treatment plants, elbows are supported by concrete anchors. In hydraulic system, high velocity bends must resist pulse reaction forces. If these forces are ignored, the pipe can shift, leak, or even burst. Momentum analysis suggests that pipelines remain safe and durable. Slide 8. Importance in engineering design. Understanding fluid momentum is very important in engineering design. It allows us to calculate hydrodynamic forces accurately, and just supports can handle those forces, optimizes hydraulic structures, and improves energy efficiency. It also reduces maintenance cost, supports sustainability in water system. Slide 9. Reflection on and sustainability. From this topic, I learned that the momentum principle is very useful in real-world engineering. Even a small change in flow direction can create a large force that engineers must predict accurately. As a future civil engineering technician, this knowledge helps me design safe water systems, prevent failures, and apply sustainable practices in engineering. For the conclusion, the momentum principle connects Newton's laws with real engineering application. It explains how forces develop in moving fluids and allows engineering to calculate them accurately. Applications like curved plates and pipe bends show how this theory enhances structural safety and efficient design. By mastering momentum analysis, we can design water systems that are safe, efficient, and sustainable. Thank you so much.